I'm going to warn you now, there's a lot to talk about in this video. Geometric proofs are not the sort of thing that fit into 2 minutes. Okay, think more like 6, 7, 8. And if you're in this kind of problem in a test, if you understand things like parallel lines and the consequences of parallel lines, great, go ahead and dig into it. But if you're kind of lost here, this would be one of those things that you skip and come back to if you have extra time. So what are the consequences of parallel lines? Well, I want to draw something important here, which is the line that runs transverse to those parallel lines. In other words, it cuts through them. What's the consequence of that? What happens? When you have a transverse line that cuts across parallels, it sets up equal angles in this way. That angle is going to be equal to this angle right here. Okay. Also, this angle over here is equal to this one. Okay, they're opposite angles across the transversal. So that's very, very useful. There's something else going on here, which is that I'm going to set up this parallel lines here. This is one of the major topics of this proof. Parallel lines. You have to know the consequences of that. The other interesting thing is if you add up all these angles that I just swept my arrow through, the sum has to be 180. Okay? So this is a 180 degree separation. I'll just call it like that. Meaning, if I put this in algebra terms, what does that mean? It means the angle ABC plus the angle BCD equals 180 degrees. Okay, it has to because they're parallel. And if it weren't 180, then they would eventually hit and they wouldn't be parallel because they'd be intersecting. Okay, I think that's all we can squeeze from the parallel lines. Let's move on to the bisector theorem. Okay, this is my angle bisector. That has a very important consequence, which is that if BD, this line right here, is a bisector of this angle, that means it cuts that angle into 2 equal halves. And it also cuts a line into 2 equal halves. So these two lines right here are congruent. They're just each half of the AC total line. And these angles right here are equal. They're each half of the ABC angle. All right? That's the effect of the angle bisector. And likewise, on the other side, if you look at the red one, same thing. This is another angle bisector. And it's going to do similar, it's going to have similar effects. It's going to cut this angle right here in half into equal parts, and it's going to set up congruent lines like so. Now, here's where something interesting happens. The bisector theorem is going to interact with the parallel lines effects. Remember when I said that the sum of all these angles equals 180 degrees? Well, let's take a look at this equation right here. And I'm going to divide that equation by 2. Okay? Seems kind of weird, but watch what happens. 1/2 of angle ABC plus 1/2 of angle BCD equals 90. So what that means is this angle right here, let's rewrite this. It's not 1/2 ABC. Why, that's just angle EBC. All right? And the other side of it is not 1/2 BCD. I'm going to call that angle BCE. Okay? And those things are equal to 90 degrees, which means this stuff up here was supplementary. Okay? These angles down here are complementary. Remember, complementary angles means they add up to 90. Supplementary means they add up to 180. So I've dug into this quite a bit now, and I think we can start making statements. Oh, no, we're not done yet. See that complementary bit? Here's something cool that happens. If orange and red add up to 90, that means this must also be 90 degrees. It's the third angle, and they have to add up to 180 total. If that's 180, that means that's 90. That means this other one is 90. And if those are both 90, it means these are also 90. So I've got 4 square angles in the middle of this triangle. And that's very cool because it sets up similar triangles. This is the last major idea. Okay, you have similar triangles. In other words, once you have all equal angles, and an equal side, you know all the other sides have to be equal too, meaning this side and this side are going to be the same, as well as this side and this side. There's similar triangles all over the place in here. So now we can dive into these statements and say what's true and what's false. AD congruent to CD. Okay, look at where those are in this figure. AD is over here, CD is over here. Yeah, we just said those are equal, so this one looks okay. ABCD is a rhombus. A rhombus is a four-sided polygon with all equal sides. So that one's good. It's not a square, mind you, that's different. Squares have 90-degree angles. Rhombuses are more like diamonds. BE congruent to DE. Next one. BE. That's this line right here, congruent to DE. Yep, that was from the angle bisector theorem. We got that pretty early. BCE isosceles. I don't think so. And the reason I know BCE is not isosceles is because this angle and this angle and this angle are all different things. Okay, none of them are equal to each other, which means none of the sides can be the same, which means, okay, this one is our false statement. This is not true. And then that last one, BCE complementary to CBE, that's one of those complementary angle things we just talked about. So we've got 4 true statements that we don't care about, and there's the false one.